my name is Joris Koefler. I'm a PhD student here at the MPI MiS in Leipzig.
And I'm Veronica. I'm also a PhD student here. And also today we have Nima. And could you maybe introduce yourself very quickly?
Yeah, I'm Nima Arkani-Hamed. I'm a theoretical physicist at the Institute for Advanced Study in Princeton.
Okay, good to have you, Nima. So we would like to start out slowly and all the way back from and ask you basically, is there a particular reason why you entered the field of physics or science in general?
Yeah, well, I mean, I think probably like most people who end up in science, I loved nature as a kid. Actually, I was most fascinated by animals for a long time, you know, sort of natural history. I would sort of catch frogs and toads and snakes and things like that and attempt to study them. So I wanted to be a naturalist for a long time. But I'm the child of two physicists, and I'd like to say it was my active teenage rebellion to become a physicist. They definitely did not want me to be a physicist. Also, I loved math from a young age. I loved math, and then I put two and two together that there was something you could do with your life that put these things about the natural world and the world of mathematics together. Actually, I can say very specifically the moment I decided I was going to be a theoretical physicist. I think I was maybe 12 or 13 years old, like most kids of that era in the 80s, you know, I was fascinated by the space shuttle going up and down. And I'd heard this number that you have to sort of fire the rockets of the space shuttle so it goes at 11 kilometers a second to get out of the Earth's gravitational field. And you know, I wondered, how did they figure out that number, 11 kilometers a second? Did they try? 3 kilometers a second, nope. 4, nope. 5, nope. You know that. And at some point, woo, it goes at 11, right?
Some expensive.
And yeah, it sounds expensive and dangerous. And my father explained to me really basic things, energy conservation, Newton's law. I didn't know any of these things, but he just sort of sketched out in a few lines the formula v squared equals 2gm over r for how you could figure out escape velocity. And that just completely blew me away, that you could figure that out and that it was something a kid could understand and a kid could do. And now that I had that formula, I had the answer for the Earth, I had it for Jupiter, I had it for getting out of the solar system, I had it for everything in one shot. And that just kind of blew me away, that there was not only some sort of beauty and wonder in the natural world, but some kind of power as well in understanding it. And that really hooked me. And around that time, I really sort of decided fairly seriously that I wanted to be a theoretical physicist and oriented my life to start trying to do that.
And in all of this path, since you were 12 years old until nowadays, I mean, it's a long time thinking about physics, of course. Do you have any particular role model or role models that were important for you?
Oh, that's a great question, because I think probably if you ask most people, I don't know if people would have similar answers. You know, there's of course heroes we have in all of physics: Newton, Einstein, Maxwell, Dirac, these people. And you know, when I was a kid growing up or learning physics, there were these sort of gods out there, but I didn't think about them too much, other than thanking them. Thank you, Newton, you know, for giving us F equals ma. But I was sort of much more fascinated, as I said, with the sort of ability to use physics to explain things in the world around us. You know, along those lines, just as maybe a tangential comment in this direction, I was not personally especially inspired by popular books about physics. They were almost, I mean, I wouldn't say explicitly repulsive, but definitely at most neutral. Because I could tell they were not giving me the real deal, you know, and I was learning the real deal already, you know, myself, so I could figure out where the rainbows were in the sky, or where you saw a mirage, or, you know, other things that was possible to figure out myself. So in that sense, the people who were the most important to me early on were either, you know, somewhat older kids who knew things they could teach me, or, you know, I had a few fantastic teachers. I had an amazing physics teacher when I was in grade 10. His name was John Wiley, who had just gotten his PhD from the University of Toronto. I grew up in Toronto in Canada. and you know, could just tell that I was crazy about physics. And one of the most amazing moments of my intellectual life, maybe one of the most contentful sort of 90 seconds I had, was when he stared over my shoulder and saw that I was, you know, working on some complicated problem with inclined planes and balls and things like that, which I sort of love to do. And he said, you know what, all these questions are trivial. You can solve them all in one line with one method. I'm like, get out of here, that's impossible. You know, I'm the world's expert on complicated monkeys and pulleys and inclined planes. You know, you're telling me there's a way of doing it any old schmo can do? And he said, yes. And he wrote down the Lagrangian, you know, and he did the whole thing in 90 seconds. You know, he said, all you do is write down kinetic energy minus potential energy, then you write down this equation. He didn't derive anything, he just wrote down the Euler-Lagrange equation. And as he went, he said, do you know what a partial derivative is? I said, no. He said, just pretend all the variables are constant. I'm like, okay. You know,
I can do that.
I can do that. And he went away. And then I'm like, holy crap, this can't possibly work. And I remember trying it on the very first problem. It was not some Mickey Mouse problem, because I mean, I wanted to see if this thing really worked. So I did the problem of the, you know, mass on a string, spinning around, attached to a weight through the hole in the table. I set it all up. I followed what he said. I got the equations I knew you were supposed to get. And it changed my life. You know, it really did change my life, because I appreciated not only is physics amazing and you can use it to predict things in the world around you, but there's structures underneath it. There are some sort of deep structures underneath it. And that you're not done when you get the first set, like F equals ma. You can sort of keep on going and discover other things about it, that exploring the sort of structures themselves is something meaningful. Anyway, so he's an example. I mean, he was incredibly important, not like a godlike role model per se, but those are the most important people to me. It was the people directly around me. You know, when I was in graduate school, it was like the slightly older graduate students who sort of, you know, showed me all the tricks of the trade, so I wouldn't have to flounder around. I think sort of much later, when I became, you know, not only started doing research, but you know, started having plans and sort of ideas for what I wanted to spend years and years of my life doing. At that point, we could talk about the more conventional sort of role model, I guess. And there, my answer is totally cliche, but maybe, hopefully not entirely cliche reasons, is probably Einstein. And it's Einstein only because, like, Newton and Maxwell are Martians. And maybe not Maxwell, sorry, I meant Newton, Dirac. People like that are clearly have some sort of CPU and mental ability that's not comparable, certainly to me, or really most of the people. You know, Newton in the Principia would wake up in the morning and decide he wanted to calculate square root of 2 to 20 decimal places for fun, because he just discovered the binomial expansion. You know, that's not me. But I'm also not Einstein. Let me make that clear. Let me make that very, very clear. But his sort of the way he went about doing physics and was not driven by some monstrous CPU. Of course, he had an unworldly physical intuition, but he made so many mistakes. You know, he made so many elementary mistakes. He was struggling for a long time. What he had more than anything is some like unbelievable drive and will to stick with a hard problem, ignore what everyone was saying. No one believed him, no one cared, up, down. But somehow he had this sort of drive to keep on going for years and years and years until something made sense. And that I find incredibly inspiring. I mean, that's very, very difficult to do, but I've tried sort of consciously, very consciously in my life to, you know, go longer and longer periods without making progress before getting freaked out and switching to something else. And, you know, Einstein's example, you know, other people, you know, there's maybe more examples in math, Wiles, Perlman, people like that. But it's this kind of sticking to something with some particular vision of what might happen, and continuing until you get there has been in some more concrete way inspiring to me.
All right. Okay, this is also already good. We're moving a bit further into your career already.
Oh, okay.
So, and the follow-up on this would be, so one of the most prominent research aspects that came out of your research life that interests us here lots is the amplituhedron.
Yes.
Is there like a bit of a story how you came to think about it and how it developed? How did you end up defining it?
Oh, yes. I mean, it's my work, even starting in graduate school and through to about 2008. So about 15 years, the first sort of 15 years of my of my, I started grad school in '93. Okay, so that period of my life, I was not doing mathematical things at all. I mean, I was most interested in thinking about theories for what we might see at the Large Hadron Collider that sort of attack problems in particle physics. There's one of the great problems of, one of the great mysteries in nature is we don't understand why the universe is big. And that's because there's sort of increasingly violent quantum mechanical fluctuations at shorter and shorter distances in the vacuum would seemingly destroy any possibility of a macroscopic universe. And yet here we are. The universe is very big. The universe has large things in it. And those turn out to be huge mysteries we still don't understand. If we take for granted that the universe is big and that it has big things in it, this is tantamount to the existence of very large sort of hierarchies of scale between very microscopic length scale, like the Planck scale, where gravity gets strong, space-time breaks down, et cetera, and the much larger scales in the universe, all the way out to the size of the observable universe. There's sort of 60 orders of magnitude between the Planck length and the size of the universe, and many other scales that populate things in between that are very well separated from each other. And the big mystery is why quantum fluctuations don't sort of crash all those scales on top of each other. So it's not an esoteric question. It's a very basic question about the world around us. You know, when I was an undergraduate, I mentioned even as a kid, I loved math and I loved physics. I loved both of them. I just loved physics always very slightly more, very, very slightly more. But it's a very slight thing. It was very difficult for me to sort of choose definitely to be a theoretical physicist and not a mathematician. But that choice kind of affected a lot what I did, because I always had in the back of my mind, if I was going to do something more mathematical and formal, I wasn't going to do something sort of half-assed. I might as well be a mathematician if I'm going to do that. Not, you know. You know, I polarized more into questions that would have direct contact with experiment, and that's really what I focused on and what I worked on. Anyway, there's many twists and turns in this story, but in the mid-2000s, me and many other people started becoming alive to a very different possibility for what might explain these mysteries, like why the universe is big, why it has big things in it, related to ideas of the possibility that the constants of nature, what we think of as the constants of nature, and these mysteries about the vastness of the universe are related to some of the constants of nature, like the vacuum energy, the cosmological constant, it's called the cosmological constant, or the constant that controls the mass of the Higgs particle. Why these constants have seemingly absurdly minuscule values compared to what you would have sort of naturally expected them to have.
So is this about naturalness?
That's right. This is the entire question that technically goes by the name naturalness, but it's really this sort of very basic question about why quantum fluctuations don't wipe out macroscopic order. And a sort of possibility started emerging that maybe the constants are not actually constant, and they take on different values in different regions of not the observable universe, but if you're somehow in a God's eye picture, zoom out to gargantuan scales, you would see that there is a giant multiverse out there, and the constants take different values in different places in the universe. And in most of those places, if you change these constants a little bit, the universe is empty or doesn't have any matter of any sort in it or any structure in it. And so it's lethal mostly out there, but in a few tiny spots it's possible for structure and life to emerge, and that's why we find ourselves there. Anyway, it was a sort of a controversial idea. It's still a controversial idea, but people tried to make sort of more proper theoretical sense of it. They tried and they failed, and I tried and I failed. Many people tried and failed. But these questions sort of convinced me that we did need to learn, even for questions of direct relevance to experiment, you know, not questions up at the Planck scale having to do with quantum gravity and so on, that one way or another we needed to figure out how to make sense of quantum mechanics and cosmology all in the same sentence, right? That we couldn't factorize these sort of deep conceptual questions about quantum mechanics in the universe from the more practical seeming questions of the sort of structure of our vacuum. And that's a very hard question, but when you start backing up from that question, at least I found myself running into a simpler version of all of these problems where you try to, it was clear you somehow have to reconceptualize what quantum mechanics, space-time, and the vacuum are about. That's sort of That's, I think, completely clear. That continues to be clear today. But trying to do that directly in the context of these cosmological questions seemed too difficult. And so I sort of tried to back up to the first setting in which it seemed like you could do something about it. So time has to be important, just like it's important in cosmology. Dynamics has to be important. You have to think about some questions where quantum mechanics and space-time matter at order 100%, in some vivid way. And so scattering of elementary particles was the sort of obvious version of that question. I had also learned, first through the sort of famous paper of Edward Witten in 2003, with some vision for what an alternate theory of scattering amplitudes might be. I was not working in the subject at all, but I knew this seemed like a big deal. And secondly, through the work of some brilliant young people who also later collaborated with Edward about these things, including Freddie Cacciazzo and Ruth Britto, who's here, who were both students at Harvard when I was there. I knew that something was afoot in this world of amplitudes, that there are very basic facts about quantum field theory that were being understood in new ways. That I found very, very striking. I thought of myself as someone who maybe didn't know all the fancy esoterica of what was going on in field theory, but I understood the basics, I thought, cold, right? And then, I remember Freddie telling me some amazing things that were associated with the famous BCFW recursion relations, but they involved some simple properties of amplitudes that I just simply didn't know. And of course, nobody knew before they discovered them. So that I found very striking, that there was something going on right under our noses that we didn't understand. And anyway, so those were all the motivations in something like 2007, 2008 to stop what I was doing and start thinking about amplitudes. The year or two leading up to this period, it was also in anticipation of the Large Hadron Collider turning on. So I'd spent a lot of time thinking about very practical questions about better ways experimentalists might look at the data coming out of the LHC. So that's why, maybe as I said in the beginning of the Chow Lectures, the period before amplitudes, I was mostly working with experimental particle physicists. But a variety of reasons, there was kind of a hard stop. I moved to the Institute for Advanced Study, and that was also a great opportunity to just sort of become a graduate student again for a while and learn a new subject. So that's when it started in 2008. But it started with this very clear picture. I would go to conferences and say, this is what I wanted to happen. Some people were friendly, some people were skeptical, but it was a very clear picture that what we're looking for is some new way of formulating what scattering amplitudes are, where we didn't have the usual apparatus, we weren't relying on pictures of particle trajectories or the evolution of the wave function in Hilbert space. Of course, this was not coming entirely out of the blue. We had this sort of stunning success of BCFW recursion, was clearly organizing our thinking in some radically different way, even though you could, of course, derive it in principle. There's a derivation from standard quantum field theory. So you could, if you're a skeptic, say, okay, it's very cool. It's a tool, right? It's a very cool tool. You can derive it from field theory and so on. But it also looked like it was organizing things in such a radically different way that you had to be able to interpret them as coming from a different world of ideas. And so that was it. It was really kind of a 5-year period between 2008 and 2013 that kind of saw this evolution towards Amplituhedron happen in steps. I spent a year with Freddie Cacciazzo visiting me at the Institute. I like to tell Freddie that I was his grad student for that year. I told him for a while, I would be his best grad student ever, but he's had really good grad students since, so it might not be true. But I learned an enormous amount from him in that year, and we started doing some work together that started thinking about what these recursion relations like BCFW meant in twistor space. That was the sort of first step. And then that led us to sort of drawing pictures for how we thought about these things in a twistor space that looked eerily similar to pictures that one of my real heroes in all of physics, really heroes in life, Andrew Hodges at Oxford, had been drawing since he was Penrose's student in the 70s. Okay, so I'd been staring at Andrew's papers that had been sitting on my desk for 2 years, for these 2 years, I couldn't figure out if he was a crackpot or a genius, and it was the latter. But it took 2 years to figure that out. And Freddie and I and some of my students back then started figuring out the pictures that we're drawing looked a lot like Andrew's pictures, and we spent a number of weeks with our crappy pictures on the board on one side and his beautiful pictures on the other side, and asking, what would we have to do to our pictures to make them look more like Andrew's pictures? And along the way, discovering all sorts of wonderful things. That ended up connecting to Grassmannians in some way. So so understanding those pictures ended up connecting to Grassmannians. That was a whole other fantastic set of coincidences that Alex Posnikoff had worked out, essentially what the structure looked like just a little while before we needed it. But we ran into Sasha Goncharov, is incredibly important in having us think about these things properly. We spent months interacting before we knew any of these things with Pierre Deline at the Institute, who who's another hero. I mean, he's one of these people. It's hard to be a hero because he's on a different plane. But still, incredibly important, sort of getting us oriented and thinking about things the right way. And so that was a sort of penultimate step. So we figured out how all the building blocks for amplitudes were organized according to concepts in the Grassmannian and the positive Grassmannian and so on. And that was a sort of, then the final step was to sever all ties to standard notions of field theory. So everything up to that point, you could, if you wanted to, still connect everything back to some relatively conventional ideas in field theory. And so there was like a last period of 1.5 years or 2 years where we struggled a lot to see where all of these pieces, the ways of building amplitudes by putting together pieces. The pieces could be thought of as in terms of BCFW, or they'd be thought of in terms of on-shell processes, or they could be thought of in terms of building blocks in the positive Grassmannian. But they're all still kind of Lego blocks that were being assembled in some way, but we didn't know what they were assembling into. And so that was maybe the most, everything up to the point I was describing was a joyride, because everything just worked, more or less out of the box. It just worked. You just had to sort of head in the right direction, and it was like walking through an open door, almost. The last period was much more difficult, because somehow 2 or 3 ideas had to exist in your head simultaneously in order to see the right thing to do next, and it took us a couple of years to see it. But even then, it was not totally hopeless, because so many little miracles had happened that we just knew the thing that we're looking for had to exist. And there were sort of experimental, there were miraculous identities that the amplitude satisfied, lots of little numerical experiments that made it clear that the kind of object we're looking for had to exist. So there's a reason not to give up, even though it wasn't clear what it was. Anyway, so that's the story. It was about a sort of a 5-year period. From 2008, where it all started, to 2013, when we ran into the object.
Then maybe fast forward and then 10 years from 2013 to, let's say, 2023, 2024, sort of this ERC grant, among which this Chow Lectures make part of, the Universe Plus grant, came to be. And we wanted to ask you, in your eyes, what is the most exciting aspect that has came out of this Universe Plus grant so far?
Well, I mean, I think it's to start with, I'd say its mere existence is exciting. I mean, it exists because of a large number of kind of scientific things that have happened over the past 10 years. I think for me personally, the story of the Amplituhedron was sort of crucial for seeing that some vision of this sort for what the laws of physics might look like is possible, right? But of course, it was for a very limited set of theories, in very special cases, and so on. You could say as many diminutive things about it as you wanted, and I would agree. So the goal was always to get closer and closer to describing reality. My attitude about this as a physicist is that as we get closer to the real world, we should expect to see more magical structures, not less. And that maybe contrasts a little bit with the attitude of some more mathematically minded physicists who say, well, you know, you see exciting mathematical structures in toy models that have some properties, they're integrable, they have this, they have that, but it's sort of cool things about mathematical physics. It's unlikely you're going to see something like that in the real world. My attitude is the opposite. You know, the closer we get to the real world, it has to get, there's nothing more magical than the real world. So it's very unlikely. If you believe in this deep connection between the Platonic mathematical universe and the real world, which I certainly do, then it's just impossible to believe that if there's something magical in a little corner, that there isn't something vastly more magical actually going on in the real world. So that was a belief, but it was only a belief, and you know, in various steps, we started seeing things with the kind of character of the story of the Amplituhedron, but quite different in technical realization, emerge in the period after 2013. At the same time, so first, even purely within physics, similar ideas started emerging in cosmology. So, that should surprise you. That you know, it should seem, at least on the face of it, surprising there's any commonality between scattering elementary particles and lying your back and looking at the night sky and sort of correlating what's happening here and there and there. They don't, on the face of it, seem to be similar problems. Of course, technically, they're very closely related. They're both computed in the same kind of you know, quantum field theory formalism. And it turns out in a very precise sense that these sort of correlations you observe in the sky in cosmology swallow and contain the formulas that give you scattering for elementary particles. So they end up being more closely related than you might think. But anyway, similar kinds of pictures, similar sort of combinatorial geometric pictures for what might be explaining cosmological correlations started emerging in this intermediate period. And finally, this is when it sort of happened that my dominant collaborators went from being theoretical physicists, theoretical physicists, to being mathematicians. And that really blew me away. I mean, you know, that they're an amazing group of people, brilliant. Of course, think about things in totally different ways than I do. And the most fascinating thing to me was that we are not in one of these typical situations, either where the mathematicians had figured everything out already and then the physicists came to use it as a tool, which is maybe the most common way this interaction looks like, or the sort of interaction where, you know, physicists know quantum field theory and string theory and can predict all sorts of things, and mathematicians have to come and figure out how to prove it later. Where, well, maybe mathematicians care about the proving it part, but if you're a physicist, you're like, I'd rather know how to make the correct statements. But this is not either one of those. It's a bizarre situation where time and time again, I mean, I mentioned the story of Poslikov and the positive Rachmaninian right when we needed it, not 50 years before, you know, like a few years before. But it just keeps happening over and over again. It's like we're running into the same beast from different directions. It's utterly bizarre that it's happening roughly, you know, simultaneously. And it means that when we talk to each other, it's useful. You know, it's not just interdisciplinary conversations because it's cool to be interdisciplinary. Far from it. You know, we're individually experts in what we do, but we're being dragged to some common boundary because we're seeing the same thing. And it's been incredibly exciting working with like a large number of different groups of mathematicians. So the answer to your question, I think, just the existence of this project that's supposed to bring together cosmology, particle physics, mathematics, in this you know, in this joint area where something clearly is happening, I think is remarkable. You know, if you told a collider physicist 15 years ago that Grassmannians and cluster algebras and, you know, total positivity of matrices with all positive determinants had anything to do with anything, they would think you're insane. You know, I mean, this is not one of those, you know, it's not one of those, you know, things between math and physics where you kind of see, yeah, probably they'll be related. It's just insane that these things are related. And if you told the combinatorialists that what they're doing, playing around with like pictures of permutations had anything to do with what's going on when you collide particles out there in nature or at accelerators or whatever, they would also think you're insane. So the fact that it's true is remarkable, and so I think it's just exciting to have more systematic attitude about it. Having said that, there are a couple of specific things, really specific sort of dreams that at least I'd had, that you dutifully put in these proposals. We are going to do X, Y, Z, W, which of course you have to put something in a proposal. But when you're doing research, you go wherever the hell the research takes you, right? But a couple of the things just happened. Much earlier than I expected. One of the things that I've been looking to do since 2017 is find a more, I'd mentioned back in 2017, we'd found some very simple toy example of one of these geometries that might be relevant for cosmology. But we did not have a sort of a complete picture of a geometry that might be, that might sort of capture all possible processes contributing to a cosmological observable. Even in a toy model, and we ran into that object back in December. So that was something. I mean, I had no idea how long it would take to find it, but I certainly tried for many years and failed. And we, via a few happy accidents, ran into it in December. Before that, something else we were talking about in the proposal, which I equally thought would take years and years to find, but happened very suddenly and very, very quickly, is some sort of version, some friend, some cousin of the Amplituhedron to describe directly the sort of gluons, the particles and the strong interactions in the real world, not in toy models. And there were a number of ideas that had been developing with collaborators over the course of the pandemic that had a sort of another approach to thinking about all of these questions involving a different set, related but rather different set of mathematical and physical ideas. But again, they were for very toy theories, and I thought, okay, after we get the toy theory settled, we'll start again, after more work. And it was again like going through an open door. It turned out to be much closer, in a surprising way, much closer to sort of connect these toy theories to really realistic theories that describe actual parts of the real world than I thought. So those are two things I'm extremely excited about. I did not expect to happen as quickly as they did. But there are several more things that we promised we'd like to figure out. I mean, really our goal is to try to describe all of nature from this point of view. We're very far from doing that, but we're working on it.
All right. I think just building on that, do you think beyond what you just mentioned, which tied some toy models closer to theories of nature, is there something other than that example you gave, which in recent developments got you excited of pushing further and further into the theories of nature?
Yeah, I mean, there are clues lying around for what might push us further in that direction. I would say that maybe the main qualitative large open problem is how. So far, this point of view starts with very primitive questions, right? So for example, if you're talking about a scattering of elementary particles, what we're doing is we throw some particles in from far away. They're moving in some directions. They have some energy. They have some momentum. So you specify their momenta. That tells you, Einstein tells you their energy. So a bunch of momenta, little three-dimensional vectors saying the directions they're coming in. Abracadabra, something happens, and then a bunch of things are going out. So that's the data of the problem. You get a function, literally a function that depends on these three vectors, these three vectors that specify the particles going in and the particles going out. And the kind of normal apparatus of physics, a normal way we think about these things is by thinking about the trajectories of particles moving in space and time and interacting. And that, of course, has all of physics in it, right? So particles are moving in space and time to get close to each other. So there's a notion of distance when they get close to each other. When they hit each other, there's some interaction. Then they produce something else. They decay and so on. So there's a sort of whole picture that involves all the apparatus of of modern physics to figure out what the answer is. But you see, all of that apparatus lives kind of on the inside of this scattering process, in the inside of the space-time when these particles are thought to be moving and so on. The actual question is not posed on the inside of this region of space and time. It's just a question about a bunch of vectors coming in and a bunch of vectors going out. So that's the canvas in which we're trying to build a mathematical universe, an alternate picture for what could be describing this process. The canvas is just, you have 7 particles involving the scattering process, 7 three-dimensional vectors. That's the space. So you have to figure out what to do in this world of like a bunch of vectors. And it seems like an empty and austere world where there isn't much to do. But it turns out with a very, very few extra assumptions, there's just enough structure in these spaces where something kind of magical can happen. But one of the most important elements that has allowed this to happen in the mathematics is that you imagine that these vectors are not just handed to you sort of randomly. Here are 7 vectors, but they're handed to you in some order. Here's a vector for particle 1, then particle 2, particle 3, particle 4, and so on. It seems like a completely innocuous, tiny thing, but being handed in a particular order turns out in physics to be closely related to the particles having what we call color. So in the strong interactions, the particles can be thought of as having colors. And the way the colors flow from one particle to the next is responsible for this ordering. So all of the progress, at least all the progress that this line of thinking that I've been involved with has been centered around involves thinking about particles with color. Now, a lot of particles in nature have color. The strong interactions, there's a notion of color. The weak interactions, there's a notion of color. This notion of color is ubiquitous. But some of the most important things don't have color. There's no notion of color associated with photons. There's no notion of color associated with gravity. And so trying to understand how we have a picture like this when you don't have color, and you don't have a notion of sort of ordering, is a very deep and basic one. Because it seemed like it was the lifeline that let something happen out of seemingly nothing. And so we really have to go back and ask, if there does not seem to be anything, if there is no color, what could be the organizing principle that lets us know what to do next? That, I think, is the sort of largest open problem. That's one. I mean, we can say we'll study it. We can say that we'll work on it. I've studied it and worked on it off and on for 10 years. You never know what kind of set of accidental and happy coincidences will happen along the way that might give the key for where to go next. But there is in this new set of ideas, there is like a clue that at least at the level of combinatorics, the world of gravity of uncolored particles is sort of sitting there in the structures that we're talking about. That's very encouraging. So it's not only is it not absent, it's sort of very much present. It's very much present, but in a very confusing way right now, in a way that we don't know how to sort of turn into formulas that physicists care about, formulas for scattering processes. But they are sitting there, and so that's why I sort of feel if we tromp around in this neighborhood for a while, we might find the right clue to let us make progress. But I think that's the sort of biggest, the most exciting question, the biggest sort of potential obstacle to the whole program, but one where there's some possible clue for making progress.
Sort of tying in also to something you mentioned, you've mentioned all along the interview, you have definitely been a key figure in pushing interdisciplinary research between mathematics and theoretical physics. Why do you think this is important? And how could we make physicists and mathematicians engage even more with each other?
Well, I have a kind of maybe a funny attitude towards interdisciplinarity, which I've maybe mentioned before. Mm-hmm. I've always been personally suspicious of interdisciplinary work. I sort of prefer to think of it as cross-disciplinary than interdisciplinary, mm-hmm. By which I mean I'm suspicious. I'm not saying like actively hostile. I literally mean suspicious, because I know many examples of people who are sort of professional interdisciplinarians, which they mean they permanently live at a boundary between two fields. And then in almost all examples I know, when you like, if the fields A and B, when you ask people in field B what they think of the work of this person, let's say, oh, they're an expert in A. And when you ask the other way around, they say they're an expert in B. I don't like that so much, that I prefer cross-disciplinary, because it means that there's someone who's, science is hard, right? We specialize for good reasons. But the bad thing about, the worst thing about specialization is not that you have to sort of drill deep and know, one thing in order to make a progress. That's all true. That's life. I mean, that's where we are in the 21st century with our with the way science works. Is if you do that so much that you sort of become blinded to other things that are going on elsewhere. You don't even sort of hear about them. They don't sort of enter your mind. But it can happen. It does happen that the exigencies of your own little thing that you're working on, force you to a boundary, right? And it's even more exciting when they force other people on to the same boundary, and you don't quite know why, but something has dragged you there together. That's definitely been the sense of this subject. That's why I mentioned before, it's not 15 years ago, it would have been insane to think that combinatorics and particle physics and geometry have anything to do with each other, but people were dragged there together. Once that happens, I think it's extremely exciting because you're not just there for the sake of being interdisciplinary. You were dragged there for a reason, and you want to talk to each other because they know something that you need, and maybe vice versa. I have to say my interactions with mathematicians have had none of the sort of stereotypical flavor that you sometimes hear interactions between mathematicians and physicists have. It has not remotely revolved around the axis of physicists on the frontier not caring at all about rigor, and the mathematicians caring about rigor and dotting all the I's and crossing all the T's. Not remotely. I mean, it's not like that at all. Of course, they care about rigor and proving things more than we do, but it's a sideshow. That much more interestingly, there's kind of a creative tension between trying to make definitions and precise versus not. I mean, as a physicist, I'm always a little nervous about making definitions precise because I always worry that we're trying to make things precise too early. And that if we just wait a little bit longer, we'll see what the sort of correct structure is that we should be talking about. So I don't want to commit too early. As a physicist, I also had the prejudice that I was right, But I've learned on a number of occasions that my friends on the other side were right, that there was sometimes, this is a good time to stop and try to be very precise about what we're talking about. Because once you do that and you find something that works even in all the degenerate cases, then something really good has happened. So that's something that I have certainly learned from interactions with my mathematical friends. So even sort of culturally, that there are some very useful parts in the way they are thinking about things that I've definitely digested. I suspect that they've picked up some things about the way we go about doing things as well. So it's been amazing. I mean, just and not at all. I've found sort of no sort of cultural conflicts. Even we don't understand each other has been relatively minor. I mean, of course, that they have a different language and so on. But precisely because it's clear we're seeing the same thing, it doesn't take very long to say, okay, you use these words, we use this words, but is it about some matrix? And does the matrix look like this? And do you do this thing with it? It's like, yeah, that's what it looks like. Okay, great. You call it this, we say it this other way. But it sort of quickly settles down to something. It's just been wonderful. I think the main thing is to just bring them mathematicians and physicists who actually have common interests into contact. Really more than anything, it's into physical contact and talking at a blackboard. I think this is one of the kind of stupidest things about the way a lot of academia is set up, is to make informal interactions that last longer than 5 hours or 2 days or a week, difficult, right? And some of these things just can't, if you've learned a subject in grad school and you're talking to someone working in an adjacent subject, very adjacent subject, you can maybe have a conversation over lunch, and then something good can happen. But if the fields are farther apart than that, even a lunchtime conversation is probably not enough for more than superficial exchange of words and ideas and so on. I found the sort of biggest barrier to working in this kind of field is the kind of 2 weeks, 1 week, 2 weeks, sometimes a month it takes to learn something. And if you have to learn it by reading someone's papers, forget it. It's not going to take a month. It's going to take 6 months, a year, God knows, right? But you have to get together in the same physical location at a blackboard and talk for a day, 2 days, a week, however long it takes until there's actual connection. So it's a very simple piece of advice about how this interaction can be improved, but I think it's probably the most practical one.
Yeah, so perhaps to wrap it up, if something comes to mind, do you have a favorite anecdote from your days in doing research or your own studies that comes to mind that you?
Oh, there are way too many. I mean, maybe I'll say some. I mean, it's one example. It's one example of many. But I'll maybe say this story because it's illustrative of a number of the things that we're talking about. So early on in the story with Freddie Cochazo and my students, where we're understanding the connection between scattering amplitudes for gluons, the work of Andrew Hodges, and the first stumbling into some connection with the Grassmannian that kind of blew our minds. Actually, the mini story there is that we didn't know what a Grassmannian. I didn't know what a Grassmannian was, but we had matrices. We had these K by N matrices all over the place that were sort of we were writing them by putting an identity block in one side and then some other things on the other side, and then we could do linear transformations on these things. We quickly realized, obviously, there was some describing some kind of k-dimensional plane and dimension, so we knew all of those things. I just didn't know the word Grassmannian, And at some point, as we're discussing, Freddie and I would say to each other, surely mathematicians know about planes and n dimensions. Yeah, surely. Anyway, Freddie was thumbing through Griffiths and Harris's algebraic geometry book, and he just found on some page a picture of a k by n matrix with an identity block and a bunch of stars on the other entries, and he said, "Look at this page." He emailed me, "Look at this page." I'm like, "Holy shit! We're doing Griffiths and Harris." Anyway. But the more interesting story is after all of this, and we were talking to Pierre Deline, who gave us 100 clues, and Sasha Goncharov pointed us in the right direction. But then we finally ran into the work of Alex Pasnikov, who had been doing. We did not know anything about it. We finally ran into the work of Alex Pasnikov, and I looked at his papers. I couldn't make head or tail of them. But you see, we had spent 6 months at this point, starting with a picture where we're gluing together basic processes where 3 gluons meet. And for good reasons, the gluons, 2 of them can be negative circularly polarized, 1 of them positive circularly polarized, or the other way around. And so we're representing the case where 2 are negative, 1 positive with a little black vertex, and the other one with a little white vertex. And so we're spending all day long gluing these black and white vertices together to make pictures that miraculously we found were related to these K by N matrices and Grassmannians and all this stuff. So then we found out that this Pasnikov guy also had these matrices and was saying lots of interesting things about them, clearly seemed related somehow. So the whole crew of us drove up to talk to him at MIT. So we got to MIT, we met him for the first time, wonderful guy, amazing guy, still great friends with him. But it was very exciting. We spent the whole morning, we had our matrices, yeah, they look like my matrices, and okay, we're clearly saying the same thing, mind-blowing, fantastic. But only about these matrices, and all these sort of algebraic structures, only about these matrices. And then we went to lunch. And in all the excitement, Alex was like, I'm a little surprised, though. In my way of thinking about things, there's some very important pictures that go along with these matrices. And we're like, oh yeah, you know, what do they look like? He said, oh, they look like this. And he drew one of the pictures that's like literally on our board, like over and over and over again for the past 3 months. Of course, interpreted in totally different ways, which we had been deliberately hiding from him because, you know, we thought that was the physics part, you know. So we don't want to bore you with these pictures. Let's get to these matrices and the Grassmannian. But that was where it came from for him as well. And then he pointed us back to his paper, where he has this throwaway comment that perhaps we can think about the little black and white vertices as something to do with Feynman diagrams. It's a completely insane thing that, of course, ended up to be not quite Feynman diagrams, but ended up being totally true, right? That sort of thing has happened a number of times. It's a great story because it illustrates so much this point that you run into the same beast. But I'll never forget that one of the great things about Alex, you know, the one distinction I'll make amongst mathematicians. There are some mathematicians, when you ask for an example, they give you the tiniest, most trivial example, right? And then for me, as a physicist, it's hard to understand something from the dead simplest example. You need to see maybe the second or third most complicated examples before you see something going on. And Alex, bless his heart, always starts with the second or third most complicated example to illustrate something. And so he happened to draw a picture that was a sort of pentagon box, and it just shocked us that it was exactly the pictures that we've been drawing for such a long time.